Welcome back to my YouTube channel. Today I'm talking about the RT function in R. The RT function generates random values from the t distribution. The required arguments are n, the number of values you want to draw from the t distribution, and the degrees of freedom of the t distribution. You also have a non-centrality parameter that you most often would not have to worry about. Okay, so I'm going to get started by using the RT function to generate 1 million values from a t distribution with degrees of freedom 10. With degrees of freedom 10, we expect the distribution of x to not be normal. And I'm going to use this custom function, HitDensity, that I made in my physically determining normality in R tutorial, with a slight modification in the x-axis. So HitDensity of x, and you will see that the distribution we generated does not match what we'd expect in the normal distribution. So in red you'll see the actual distribution of the data, and in blue you'll see the theoretical distribution. And of course we have 1 million values that we would expect these to be right on top of each other if it were truly normally distributed. So we see a higher peak right in the middle here, the mean value, or however you want to think about it. And what's less obvious is that there's a little bit more density in the tail of the t distribution, and a little bit less in the center here. And we'll see as we go up in degrees of freedom, these differences will go down. So I'm just doing this one more time. This time with degrees of freedom 20. And we see, now that I went up to degrees of freedom 20, the actual and theoretical densities are much more closely matching. The actual density is a little bit higher than the theoretical density still. The density here is still a little bit lower. And if you really try to look at it, you can see that the red line is still above the blue line in the tail. And as we know, around 30 is when the t distribution starts to look almost indistinguishable from the normal distribution. Or at least that's when we're satisfied in saying the t distribution is close enough to the normal distribution. You see the differences here on the side are not nearly as noticeable. Density here is a little bit higher, and I don't know that I could ever tell a difference between these two lines here. Okay? So as I've been doing with all of the data generating functions, I'm going to run a quick simulation just to show how easy it can be to use these data generating functions to get proportions. For example, the proportion of values between -1 and +1, or the probability of a value being in that region. And while it doesn't replace P, Q, and D, because simulation would never give you exact values, it can be a more intuitive way to think about what you need to be and give you an answer that's closer to what you would reasonably expect. Okay, so the beginning of this is setting up a for loop. So I want to iterate I from 1 to the length of x. The length of x I've set is 1 million, so it's 1 to 1 million. Okay, so I'm going for x from 1 to 1 million. But xi, really. Okay, and x is distributed as t-distribution, degrees of freedom 10. So for this, I want to get all of the density between -1 and +1, this little chunk here. So we know the normal distribution has 68% of its density right here in that chunk, and we want to see how the t-distribution with degrees of freedom 10 differs from that. So I want to make a conditional statement that if xi is greater than -1 and xi is less than 1, so that's a setup between -1 and +1, a very intuitive way of thinking about it, rather than thinking about what part of the graph I'm in. Do I need to do 1 minus whatever I get? It's a conditional statement talking about where you're at. So when the condition's met, I want my counter to count that. So counter equals counter plus 1. And then I get this value. And then think about it in terms of proportion. We want counter divided by the length of x. And we find that 0.66% of the density here is between -1 and +1. So slightly less than the standard normal, which makes sense. We have slightly heavier tails and the distribution is more spread out. There's more opportunity for more extreme values in the t-distribution. Okay, so that's all I had for today, and thank you for watching.